everyone. Welcome to the another session of digital signal processing. We had been discussing about multi-rate signal processing, in which we have discussed about two basic techniques, decimation and interpolation. Today we are going to discuss about the two applications of multi-rate digital signal processing, that is subband coding and its corresponding structure that is used to implement it, that is quadrature mirror filter. So before discussing subband coding and its structure, we must know about what is digital filter bank. So when we talk about digital filter bank, they are like any other system of bank that we use for filtering the system. That is, either a filter can be a low pass filter, band pass filter, band reject filter, according to the demand of the application. And when we talk about this term filter bank, that means we are going to use multiple array of filters to perform certain kind of classification, or you can say the segmentation of a signal, to achieve certain kind of processing which would be done at a ease of the computation complexity. So what we do here, whenever we talk about this filter bank, it is used for performing the spectrum analysis. And second thing that we talk about is whenever we are talking about the signal synthesis. So depending upon these two kinds of performance that we want to do, we categorize these filter bank as either analysis filter bank or synthesis filter bank. So both of these type of filter bank have their application at the transmitter end, when I am transmitting my signal, maybe after processing. And second category of filter finds its application at the receiver side, where I need to reconstruct the signal and use for certain kind of application. So more or less, when we talk about the structure of analysis filter bank and synthesis filter bank, we find that they are more or less same. Only the difference is that one is being implemented at transmitter and another is being implemented at receiver. So what do we see? That in the case of analysis filter bank, when we implement it, it consists of a set of filters with system function. Say we'll use the system function as HKZ, and they are arranged in parallel form. So we have multiple filters which are arranged in the form of parallel concatenation. And the frequency response characteristics of this filter bank, that is split into corresponding number of the subband. So what do we see here in this diagram? We have two sections of the parallel structure. Let us talk about the first section. Let me rename it as 1 and 2. So the first part is, we have certain Xn signal which is composite of n number of frequencies. A frequency band, say f1 to f10 hertz of frequencies are the part of the signal Xn. So this particular composite signal is given input to array of filters which have different filter function. H0, H1, Hm-1. So we are talking about M filters arranged in parallel. Now all these filters would have their own cutoff frequency. These filters can be my different low pass filter. These can be my band pass filter according to the requirement of the frequency which I want to extract from the given signal Xn. So whenever we talk about the filter band, most of these banks would be band pass filters with different cutoff frequency. For example, this particular H0Z would be a filter function which is capable of passing out frequency F1 to F2. Only these frequency would be passed and all other would be rejected. This second bank would be able to pass on the frequency F3 and F4 only. So that means whatever I get at the output of all these would be the part of the Xn. So if Xn is having 10 different frequency, depending upon the H we have chosen, the band pass filter we have chosen, all these V0 n, V1n and V-1n, they would have a subsection of this Xn. Only 2 frequency, 3 or 4 frequencies out of the given 10 frequencies. So all this frequency which I am getting here as V0 n, or I am getting as V1n till V of M-1n, this I call them as subsections or sub-bands. And this complete block of parallel filter is I call as filter bank, and I name it as analysis filter bank. So dividing a composite signal into sub-band of frequency is something I called as analysis of signal. So this is what we were talking about, that the frequency response characteristics of this filter bank splits into corresponding number of the sub-bands. This particular digital filter bank can be represented as set of digital band pass filters that can have either common input or summed output. So common input we'll be discussing when we are talking about analysis, and summed output when we'll be talking about synthesis. So signal Xn, it is decomposed into set of n sub-bands. We have named them as VKN, and with sub-band analysis filter bank. After obtaining all these V components, as we have seen in this diagram, what we have to do, these sub-band signal, they occupy a portion of the original frequency band of Xn. And when we combine them together, we'll be able to create the approximate version of this Xn using synthesis filter bank. So the second section that we have seen in the block diagram, that correspond to combining all these components here as a summer and giving the output Yn. So this second part is my synthesis filter bank. So this is again the array of filters, some kind of bandpass filter. So all these input would come from here. If we talk about its direct transmission, they would be processed here, and all the process signal, whatever I am getting here, would be added together, and this Yn would be obtained. And I assume that this Yn should be as close to Xn. Practically it is not possible to have the exact replica of Xn, but approximate version of this Xn. So this second part is synthesis. In between, when this V node reaches V node cap, we have the phase which is called as transmission, and before this transmission, I can process this signal. So in transmission, the signal may vary. In processing, signal may vary. That's why there is little difference between V node N and V node cap N. So talking about digital filter, we are simply talking about these filter bank as analysis filter bank and synthesis filter bank. When analysis filter bank is present at the transmitter side, the synthesis filter bank is present at the receiver side. So in the subband case, synthesis filter, this V cap N, which belongs to the contagious frequency band as we have received from the analysis filter, here I'll be obtaining Yn as the output of the synthesis filter bank. This can be done by combining various synthesis filter with some system function which is being represented by AK. So AK and HK are only the distinction of the name. H is being used at the transmitter side and A is being used at the receiver side. So these kind of filter banks, they find their application where the input signal is splitted into number of the consecutive bands in the frequency domain so that each subband can be independently processed. So when I am dividing this Xn into smaller bands of frequency V1, V2 and V3, what ease do I have? Rather than processing all the frequency of this composite signal together, I can treat each component independently. So I would be able to perform more accurate processing. I would be able to eliminate the effect of finite word length effect because small number of frequency range would be there. The memory requirement would also be reduced. So the main aim of doing is to significantly reduce the number of bits that we use for representing the original signal Xn for storing or for transmitting purpose. So when we store them, we are saving the memory, and when we are transmitting it, I'm saving the bandwidth. So what is subband coding of the speech signal? It is more or less same as the implementation is in the form of the digital filter bank. So whenever we talk about this multi-rate filters, where we're talking about different frequency band and every frequency is being treated differently, this gives a useful idea of filter bank without filters. And this is having multiple bandwidth. What is the benefit? First is quantization noise is localized in the subbands only. Signal to quantization noise ratio is improved. Why? Because independent variation of quantization step size in each band. I can work with different sampling frequency, different quantization and step size for each frequency band that we have created using analysis filter bank. So that flexibility would also be there. And whenever we'll allocate the bit, that can also be done on the basis of different criteria on different frequency that we have obtained as subband. So the subband coding system have been proven to be powerful tools for data compression schemes such as MP3 and JPG 2000 format, for denoising and for signal estimation. So more or less every application would be implementing this subband coding in the form of the filter banks. This complete operation has two functions. One is upsampling and another is downsampling. So this is a structure where we see two parallel rows performing the same operation. If we talk about this first row, the first operation is my decimation by a factor of 2. It is not compulsory that this decimation would be by 2. It can be by any integer m. And this second case is for interpolation by 2 or interpolation by any factor m. So decimation is proceeded by interpolation. The same thing is repeated into the second branch. So we can have multiple such branch attached into the parallel, in which I am performing first decimation and then I am performing interpolation. This is similar to like I'll be implementing decimation at analysis side and I'll be implementing interpolation at the synthesis side. So when do I combine these two things? Analysis filter bank and decimation, synthesis filter bank and interpolation. This complete process is what I call as subband coding. So here the top branch is downsampling and the bottom branch is performing the same operation but on a delayed version of the signal. So here I have combined here these H node and C node are my filters, basically bandpass filters, and these branches are having decimation by 2. Here I have interpolation by 2 and here I have again a set of filters. So this is a block diagram representing the subband coding of any kind of signal, maybe speech signal, maybe video signal. So this first section, which is having a junction of these filters plus decimator, is analysis part of that application, and which is having interpolation and a set of filter is the synthesis part of the system. So every system would analyze the signal and synthesize the signal. Why we are decimating? Because whenever we are analyzing with the system, we would require few number of samples to reduce my memory requirement. And at the receiver side, I'm increasing the number of samples so that the signal which I'm generating or reconstructing at the receiver side, that would be the exact replica of that we have transmitted. So intermediate to the processing, I'm reducing the number of samples, but when it is the time for representing the signal at output for certain application, I need a good quality signal. So I have to increase the number of the samples. That's why decimation is the part of analysis and interpolation is the part of synthesis. Now quadrature mirror filter, these are nothing but when I want to perform this operation of analysis and synthesis, this is one special structure which is implemented. So in application, wherever we want subband filtering, the processes are carried out in a sequence. The sequence is the signal Xn is split into number of subband signals, say we are representing it as VKN using analysis filter bank. Then these subband signals that we are getting here as V1, V2, V3, they are processed. Now this processing can be any task which I want to apply onto my signal. Say I want to encode my data. So coding can be performed. And after coding, it would be transmitted. And the third step is the process signal. They are combined using the synthesis filter bank to obtain the signal Y. So only these three steps are the part of subband coding. And the subband signals, they are downsampled before the processing, and the signals are upsampled after the processing, and this entire flow of process is implemented by a special structure, and that structure is called as Quadrature mirror filter bank. So let us see how this structure looks like. This particular structure is for 2-channel QMF, but necessarily we do not have 2-channel, it can be M-channel as per the requirement. So what this particular thing says over here, the critically sampling filter bank, the decimation and interpolation factors must be equal. So here in this diagram, we are showing it by 2. It can be any value M, it can be any value I, but M should be equal to I. So if I am decimating by 5, I have to interpolate by 5. In that case, we call it as critically sampled filter bank, where we get the more accurate output as compared to other combination of I and M. So this QMF filters, because they are the application in the subband coding. So very first application is the subband coding of the speech signal. Also we are using it in the image processing, in antenna system, in wavelet transform, wherever we are applying. So wavelet transform is nothing but subband coding of any kind of signal I want to process using wavelets. Also in the biomedical engineering and digital audio industry. So more or less every application is being implemented using these structures. So talking specifically about 2-channel QMF bank, it would split the discrete input signal into 2 subbands having equal bandwidth. So if I have a signal XN with frequency say 1 to 10, then it would have 2 bands having frequency say 1 to 5 and then having 6 to 10. In this way it would, or it is a band say 0 to 10, then it would be better to say 0 to 4 and 5 to 10. So their bandwidth of 2 subsamples or subsequences we are generating, they would be equal. Then we'll be using low pass filters and high pass filter analysis filter bank to generate these 2 subband signals. So XN would be inputted to a low pass filter. Simultaneously, it would be passed through the high pass filter as well. These subband signals are then decimated by a factor of 2, which is not compulsory, to achieve the signal compression or to reduce the processing complexity. The decimated signals are then encoded and then it is transmitted. Similarly, at the receiver section, the 2 subband signals, they are decoded and then they are interpolated by a factor of 2. So this factor would remain same at transmitter and receiver. And finally, they are passed through the low pass filters and high pass filter synthesis filter. And finally, I get my XN signal, approximate value of the signal that I had transmitted. An output of all the synthesis filter bank that is combined together to have the reconstructed signal YN, which is approximate copy of XN. So stage by stage we can see here, this is XN, the composite signal. These are 2 filters. So V0N and V1N, they are both signals having the same bandwidth. Then we are decimating these 2 signals by a factor of 2. This is the first section where I am obtaining U0N and U1N, and this section is what we call in the language of subband coding is the analysis part. So this XN, when passed through this H0Zen, this V0N is the convolution of these 2, H0Z convoluted with XN. Similarly, this V1n would be the convolution of the transfer function is H1z. It is convoluted with the input signal Xn. These V0 and V1, they are decimated by 2. So what is the characteristics of these two filters? If one is low pass filter, then this has to be my high pass filter. Then only these two would give me the contiguous frequency band. Say one is passing 0 to 5, another is passing 5 to 10. So looking over here in this particular derivation, V is the convolution of the transfer function and input signal. Then it is decimated by 2 and I am getting U signal. And finally, if I talk at the second part of the section where this is interpolation and another set of the synthesis filter, I am getting Yn. So V cap n is representing the interpolated signal. So U is interpolated by 2 and I am obtaining V cap n. So V cap n is dependent upon UK. So in these simple stages of simply filtering the signal, generating the small bands and then decimating them is the one part of the analysis. The obtained signal are interpolated and then again filter out and combined is giving me the synthesis part. So these three equations are combined, solved and rearranged. The final output which I get here is 1 by 2 TZ XZ and BZ X of minus Z. So why these two systems are negative of each other? The only mathematical significance is that when I'm talking about the analysis filter bank H0Z in the diagram, this is low pass filter and H1Z is the mirror image high pass filter of this low pass filter. Then only I get the contiguous frequency bands. To represent this in the form of equation, if H0 omega is H omega, then H1 omega is omega minus pi. So this is low pass filter representation, this is high pass filter representation. Or in the time domain, the condition is like H0n is equal to Hn, so H1n is minus 1 raised to the power n Hn. So in the diagram we can see over here, we are talking about these two filters. And these two filters should have a characteristics. This first is my H0 and this second characteristics is my H1. And their intersection point is at pi by 2. So one here is working as low pass filter and second here is working as high pass filter. So if I am following this property, then I am able to generate the accurate subband which are contiguous in frequency and we are not losing any part of the frequency when I am performing this analysis, and there would be no loss of information even after decimation. So the cutoff frequency for two filters is here at pi by 2. Subband signal Vk, they are downsampled. After downsampling, these signals are processed. We can encode them or apply any other kind of processing. At the receiver side, the signals are decoded, they are upsampled or interpolated, and then they are passed through synthesis filter bank. And the name of these filter bank are C0 and C1. So as we see here in the diagram, we are talking about this C0 and C1. And as I was telling you that analysis and synthesis are almost same. So these characteristics of these transfer function would be related to the transfer function H0 and H1. We'll see this in the next discussion. That when we talk about errors in the Qmf filter, so whatever processing we are doing, we are trying to decrease the number of errors in the analysis or in the processing. But whenever we are synthesizing here in this diagram, in the second stage, there is the probability of introduction of certain errors. What are those errors? The reconstructed signal suffers from three types of errors. One is aliasing distortion, second is amplitude distortion, and third is phase distortion. This is because the filters that we are using for the processing, they are not ideal. So in most of the application, the common requirement is that the reconstructed signal should be as close as possible to the input signal xn. That means the condition we are talking repeatedly, that yn should be approximate version of the xn. So what we have to do, the main stress when we are designing this QMF filter has been to eliminate or to minimize these three distortions to obtain a perfect reconstruction or nearly perfect reconstruction of the system. So what can be the possible condition that we are able to reduce these distortions or errors which are being introduced? We have to see that this QMF filter structure is linear and time varying system. Why? Because the process involved upsampling and downsampling, that is also linear time varying. And when we talk about this analysis and synthesis filter bank, we have to choose them properly so that aliasing effect is reduced. So what should be the choice of these filter? This is a particular condition we should be satisfied when I'm designing the QMF filters, so that there is no aliasis or minimum amount of aliasing in the signal. What is this condition? The product of H naught minus Z and C naught Z. Let me look what this is being shown in the diagram. H naught is this, and I'm choosing certain C naught and C1. What combination of these transfer function is going to give me error-free output? H naught minus Z, C naught Z plus H1 minus Z and C1 Z. That means all the two branches, the transfer functions, their multiplication and addition is equal to twice of BZ. From where do we have obtained this? From this particular equation, which we have obtained from 3 stages of subband coding that we have performed. So this BZ is nothing but this is this part of the equation, which is H naught minus Z, C naught Z, H1 minus Z and C1 Z. This part of the equation, if it is 0, I am able to eliminate the effect of aliasing. Putting this equation equal to 0 means C naught Z should be equal to H1 minus Z and C1 Z should be equal to H naught minus Z. That means the filter I am using in the first branch of synthesis bank should be the mirror image of the filter I am using in the second branch of analysis filter bank. Similarly, the second row or the second filter I am using in synthesis should be the negative of H naught minus Z. So if I choose the characteristic of these 4 filters, 2 in the analysis side and 2 in the synthesis side, so I'll be able to eliminate the error arising because of the aliasing. In this case, if I put this BZ equal to 0, then this YZ becomes TZ and XZ. So looking at the main equation, if I put this BZ 0, that means this entire factor becomes 0, and the standard equation I'm left is 1 by 2 HZ C naught Z plus H1Z and C1Z. This entire part has disappeared. So here I can see this distortion factor TZ is dependent only onto the factor H naught H1, and the C1 and C dot can be replaced with H1 minus Z and H naught minus Z. So I have to choose the characteristics of only 2 filters, H naught and H1, and in the synthesis side I have to use the same filter but in the negated side. The transfer function would be negative of H1Z and H naught minus Z. So using this particular choosing a filter with the proper characteristics, I may be able to eliminate one of the 3 errors mentioned here in the problem, that is called as the aliasing distortion. So more and more research has been being done so that these kind of structures can be improved. Like the QMF filter bank, we have the conjugate filter bank, and my effort is only to decrease these 3 kinds of error, to have the output signal which I am reconstructing out of the entire structure that would be free from any kind of noise and distortion. This was all about my multi-rate digital signal processing and its application. That's all for this session. Thank you.